Okay, so now that we have done this, I'm going to switch tracks a little bit and we're going to look at something in MATLAB just so that you get a feel for visualizing these entities. Okay, so I'm going to take a function which is beautiful to visualize. Let's just note that down. Function of two variables for the simple reason we can visualize a three-dimensional plot, right? So e to the minus x minus 1 whole squared sine pi y, okay, and so does this function look periodic to you? It is periodic in which direction? It's periodic in y, right? So along the y axis I will find it repeating, and in the x direction it's definitely not periodic, right? It's a decaying exponential. So what would you say is the period of this function in the y direction? Right, 2 units. So what I'll do is we'll restrict ourselves to some region of space where the function is kind of easy to visualize. So this is what I'm going to look at. Okay. So okay, is it visible, the font? Probably not, right? So I'll just increase this. Yeah, home will have it, and preferences, right? And we go to display fonts. Is it better now? Oh, let's make it more. Is it visible at the back? Okay, so there are, I mean, I've sort of pre-written this, but let's go over it step by step. This will also give you an introduction to the symbolic math toolbox in MATLAB, which is very powerful. Okay, which allows you to do symbolic manipulation of functions. You don't have to always do numbers. You can work with symbols. How we work pen and paper math, that's how the symbolic toolbox works. Okay, so the first expression over here which I have highlighted is simply declaring x and y to be symbolic variables. It means that when you encounter x and y in any expression, it is a symbol. Okay, so let's just run this over here. So once you run it over here, you will see that x and y will get declared to be symbols in the workspace. Okay, once I've defined x and y to be symbols, the next expression is telling me what? This is the definition of the function. I've put a 1 minus here just for convenience. So I'm saying fs is a function of x and y given by whatever I want. So in this case, I've defined it like this. Okay, let's evaluate this. It's done. So now fs has come in the workspace. Now I'm going to use the fsurf plot, which is going to give me a visualization of this function. So when I run this, it takes two arguments. The first argument is the function. The second is the range in x and y. I have to give it a range, otherwise there is some default range, right? So it's saying in the y dimension there is 0 to 1. In the x dimension this is 0 to 2, right? So this is my x dimension, this is my y dimension, right? Now this is very nice to visualize because you can see that is there a local minima here? There seems to be a local minima. It looks like a cup, right? So there's a minima here. If I had plotted this for a large range of y values, so x is going from 0 to 2 and y is, let's say, going from minus 50 to plus 50, would I have many identical minima? Yes, I would have many identical minima, and depending on which is my initial point, I'll fall into the minima into that minima. Okay, so that is the first part. Now what I want to do is, I want to visualize what do gradients look like. We have spoken so much about gradients and descent directions and whether or not the function is decreasing in value or not. So the next thing I'm going to do is, I'm going to use a command called mesh grid. Mesh grid simply is going to make a set of points in the dimensions. So here I'm giving it two arguments, 0 to 2 in steps of 0.1, that's the x grid, and 0 to 1 in steps of 0.1, that's the y grid. So mesh grid and the range of x and y values is going to create a array of x and y values, and it is going to get stored in capital X, capital Y, right? So it's done. So if you want, when we can open this capital X, it's basically a matrix of all the x coordinates of the points. If I open capital Y, it's a matrix of all the y values, right? So this is standard. Now, once I have done this, now let us say I want to visualize the gradients. So I'm going to do gradient fs. Now gradient fs is again a function. Fs, remember, was a function of x and y. When I say take gradient of fs, is going to be a function. Okay, so let's run this and see. Here you can see in the command window, it has actually evaluated the gradient. You see, it's given me a vector. There are two entries of the vector. The first, what is the first entry which I'm highlighting over here? It's gradient of f. Therefore, this first entry is df by dx. It's done what you would have done pen and paper math. It has done it over here symbolically. Remember, there are no numbers here. This is symbolic differentiation. I've got df by dx. Second column is df by dy, right? That's why this is a very powerful tool. Okay, and the next thing is, I'm going to now, I didn't put a semicolon, so it just displayed it to the command line. I want to capture it into a variable, so I'm going to assign it to g. So it's now sitting in g. I'm going to extract the df by dx and df by dy into separate variables called fx and fy, just for convenience. Okay. Now, when you have this symbolic function floating around, at some point you want that symbol to take certain values. Supposing I have f of x is equal to x squared, and I want to evaluate f at some point 5, I need to substitute x equal to 5 into that expression. That is done in MATLAB with the function subs, literally stands for substitute. So what am I going to substitute? So let's look at this command over here. So as I'm saying substitute, fx was what? Df by dx, which was this first expression, which is an expression. It's an expression, and I'm going to give it x comma y, means it's just telling it that these are the symbols that you should expect. What are the range of values, numbers that you should expect? They are coming from capital X, capital Y. That's the meaning of the substitute command. So substitute into this expression these variables, these range of x, y. Do it for the x, that is the derivative with respect to x, derivative with respect to y. Okay, so let's run these guys. They are done. Okay. Having done it, now let's plot it and look at it, right? So let's start a new figure window over here. So f contour is going to give me what? Contours of equal, contour is a contour of equal function value. So, right, let's look at it. So this is like a flattened view of the function. So if we, yes. So look at the x-axis here is going from 0 to 2, the y-axis is going 0 to 1. The blue colors, the blue lines over here correspond to the bottom of the bowl over here, right? Those are the lines where function has a low value. If you want, you can put the legend over here. And yellow has the highest value, which is 1 over here. So what have I done? You can think of this left figure just like an apple, and I've sliced it. And I've sliced it in such a way that every slice has the same value of f. That's what is called a contour. Okay, very good. Having done this, now is the fun part. I've calculated the gradients sitting in capital Gx, capital Gy. So I'm going to say hold on, which is going to, I better make sure that it was for the correct figure. Okay, we'll see. Now quiver is a plot which is going to overlay arrows. So it's going to say overlay arrows means vectors. So at the points given by capital X, capital Y, I want you to overlay arrows which are sitting in Gx, Gy. So, okay, now it's done. Let us, I hopefully, yes, there we go. Right. So on the contour plot, at the same values of capital X, capital Y, I have substituted the values of x, y from that grid, populated the Gx, Gy, and it is overlaying all the grad fx, grad fy value. When I combine it, it becomes a vector. So these arrows are actually telling me what? This is the gradient of the function. This is the gradient of the function. Not surprisingly, what do you see? At the bottom of this bowl, you can see that the length of the arrows is getting smaller and smaller. Was that not a signature of a stationary point? Grad f mod means length of the vector is small. As I am going up the bowl, the length of the vector is becoming large. That means what? Rate of change of the function with respect to x and y is increasing. So you see, as you go higher and higher above over here, as I go higher up over here, the rate of change of the function is large. That means it's a very steep something, right? So now you can see the intuition of gradient descent. So if you are at this point, let us say over here, and you want to go down to the center of the bowl, flip that arrow, and at every point follow the negative of the arrows that you're seeing, and you'll hopefully land up at the center. Okay, that is the intuition behind gradient descent. Correct. So what is being suggested that here I plotted Gx, Gy. In the definition of Gx and Gy, I could have put a minus sign. That would have given me the plots of the negative gradient, right? So this code is available on the website. You can download it and play around with it, right? Now we can do further things. We need not stop at just the gradient. We can also use the symbolic toolbox to do Hessians. So let's look at the Hessian. So this is not surprisingly going to calculate the Hessian for you. If you plot, if I just type in H over here, you can see it's a long expression. It has calculated faithfully the second order derivatives. Okay. So this is a very valuable tool in your research, because when you start calculating second order gradients with high probability, you will make a mistake somewhere. So this is a way of checking. Okay, so now what am I going to do is, I just want to explore values of this Hessian at different points in the landscape. So again, the subs command is going to work. So subs is going to say x and y are the symbolic variables, and I'm going to pick some random value 0.1 comma 0. Okay. So when I do this, so the value is sitting in H. Now this is a little bit of a quirk of the symbolic toolbox, that the value is sitting inside H, but to get the numerical value, you have to use a command called eval. So when I do that, what do I get? I get this. This is what the Hessian of the matrix is at this point. Okay. This by itself does not tell us very much. We are interested in knowing, for example, is it positive definite or not. So to do that, what do I want to look at? The eigenvalues. So there is, thankfully for us, a nice command available over here. I want to plot it. What is it? What does it tell us? So was anyone surprised over here? I was surprised. Can someone guess why I was surprised? The hint is to look at this. What was the geometric intuition of, so I mean, this Hessian, is it positive definite? It's not. When you look at this, when you look at a bowl, your intuition, it's a bowl, it's a nice parabolic bowl. So the Hessian should be positive definite everywhere, but turns out it's not. One of the eigenvalues is negative, right? So you can actually see that as we evaluated this at 0.1 comma 0. So 0 means y value 0 and 0.1 is somewhere here. So at the edge of this parabola is kind of going a different way. So this is kind of like a saddle point almost. In one direction it is increasing, in the other direction it is decreasing. So we have to be very careful with trusting how a visualization looks. You know, you have to calculate quantitatively whether or not it's actually a Hessian. Just don't go by how it looks, right? So this code is very useful for you to sort of get a feel for how do gradients look, how do Hessians look, and you have all of the tools available over here. You can cook up whatever function you want, right? If let us say you did not have this function very nicely sitting for you in X and Y format, but it came from data, no problem. You could do a quadratic fit of the function and then work with this, right? You will not have you will have symbols. The symbols will just be a quadratic form. Okay, so please play around with this code to get some more intuition. If there are any questions about this, we can talk about it. You distributed? If we were, okay, so the Hessian is not positive definite. What does that mean? Which method is a bad method to choose in optimization? Newton method is not the correct method to use because it will fail at one point. It will take you for a ride, right? So, yeah. Checking the positive definiteness is necessary for you to proceed with a Newton method. But if you are doing gradient descent, it's fine. Any other question? Yes, so very good question. So here I picked the value of 0.1 comma 0. In that neighborhood, the Hessian is not positive definite. If I had picked some other value, supposing I had picked a value very close to the bottom of this, actually I would have got it to be positive definite. How do we know whether or not it's positive definite? You never know. You have to evaluate it. If you don't, if you have some good analytical approximation or some intuition about it which you can quantify, then you can use it. Okay, but I mean that was one of the reasons I chose such an example, because it looks to be convex but it's not convex, right? So either you evaluate its second order derivative and check whether or not it's a positive definite. If that is not possible because your function is so expensive, which is the case a lot with machine learning and all, what do people do? They do not bother with Newton method. They just do gradient descent, because gradient descent will always work for small enough values of alpha. It's always a descent direction, minus grad f, it works. Price you pay is, it's slower to converge than the Newton method. But you can see in this interplay, there's a lot of scope for research. How do I pay as little computational price yet get good convergence? I mean, this is the stuff of pretty much all of DLML research, right? So for how many of you saw the symbolic toolbox for the first time? Okay, about 30%. Good. So make friends with it. It's a very valuable tool. Can you evaluate complex valued functions? Yes. I mean, when you are working with complex valued functions, the best thing would be split real part, imaginary part, work with each one separately. Some MATLAB functions are a little picky that, for example, gradient with respect to a complex variable, is it defined? Is df by dz, where z is equal to x plus iy, is it defined? It's not defined in the usual way. There is a generalization of it. So then you have to, you could either work with z or you could work with x and y separately. But in this course, we're going to work mostly with real valued functions. Once you get the full grasp of this, to generalize to complex is not difficult. Because everyone signed the attendance sheet. So police coming. Thankfully, that rang at the end of the class. So as we go in this course, if you find yourselves not getting intuition, feeling stuck, come back to a code like this and play around with it. Right? Even this graph over here which I have, you can just rotate it and play around with it any way you want. Right? So you can see blue is telling you the lowest values. So you can literally do what you want. So you can see that this curvature is kind of changing over here along this edge over here. Here is where it stops being positive definite. Yes. No, I did not say that it's only for convex functions. If the function is convex, then Newton method will be very easily applicable. In fact, if the function is quadratic, which is a special case of convex, then Newton method will give us the answer in one shot, because what we derived would be exact. So it's not for only for convex. So only thing we have to make sure is that the function is positive definite, then I can use it.